Welcome to Exponential Functions and Transformations. In this section, we will study the following topics: evaluating exponential functions with base b, graphing exponential functions with base b, solving exponential functions with base b. All right, here's the definition for our exponential functions, where b is the base and the independent variable is in the exponent. So in an exponential function, the variable is in the exponent. Which of the following are exponential functions? That is right. B and D are exponential functions. Just as the graphs of all quadratic functions have the same basic shape, the graphs of exponential functions have the same basic characteristics. They can be broken into two categories: exponential growth and exponential decay, or also called exponential decline. We will look at the graph of the exponential function that increases as the x increases, known as the exponential growth function. It has the form of f of x is equal to ax, where a is greater than 1. So notice on this table, okay, if we are with negative numbers, then our f of x value, our y values, are fractions. When the exponent x is 0, it changes everything to 1. And then as the x gets bigger, 1, 2, 3, our values also become larger. So as the graph increases slowly for x less than 0, notice the rapid increase in the graph as x increases, and you are on the right side of the y-axis. The y-intercept is 0, 1, and your horizontal asymptote is y equals 0. This is a real-life example of exponential growth. This is the number of cell phone subscribers at year's end for the years from 1985 to 2004, with the numbers of subscribers in the millions. First, let's change the base b to different positive values. So notice the first graph in red, where y is equal to the base 2 to the exponent of x. Now we have changed to the second graph in green, where y is equal to 5, base 5. And then in the third graph in blue, y is changed to the base 15. Notice how the steeper the curve is, but still you have a y-intercept of 1. Okay, let's look at a graph of an exponential decay function. We'll look at the graph of an exponential function that decreases as x increases, known as the exponential decay function. It has the form f of x equals a to negative x, where a is greater than 1. Okay, so oftentimes we don't work with negative exponents, so notice that the negative exponent changes the 2 to a 1/2. So really we're looking at fractions here, okay? A fraction to the exponent of x. So if you have negative numbers, then you wind up with whole values, okay? And then if your exponent is 0, your y-intercept is 1. Notice, though, that when the numbers are positive, that we have fractions, okay? So notice the rapid decline in the graph as x is less than 0. The graph decreases more slowly as x increases. The y-intercept is 0, 1, and the horizontal asymptote is still y equal to 0. Okay, so we're going to look at some more examples. Okay, the first example is that y is equal to a base of 0.8. The next example is y is equal to the base of 0.5, which is 1/2. And then our third example is y is equal to the base of 0.1. The closer the number is to 0, the steeper the curve. Okay, notice you still have a y-intercept of 1. Okay, notice that really our two exponential functions are really reflections of one another about the y-axis. Both graphs have a y-intercept of 0, 1 and a horizontal asymptote of 0. The domain of both of these is negative infinity to infinity, and the range is always the horizontal asymptote to infinity. Okay? So again, as noted, your 2 to the negative exponent is really 1/2 to a positive exponent. So the exponential function is a decay function if you have a base greater than 1 and the function is written as that base to a negative exponent, or if the base is between 0 and 1, and that means it's a fraction to a positive exponent. Okay, here are some examples of uh, this. Okay, so one is a fraction and the other one would be 1 over 5.6. All right, what else can happen with exponential functions? They can be transformed, okay? So in the first one, we have the blue is your base 2 to an exponent, which you can see is the standard base. What happens is, with the red one, is it's been moved up 3. So we have a vertical shift of 3 upwards, okay? This changes your horizontal asymptote because whatever your movement is, that becomes your horizontal asymptote. So in this case, it's 3. And then in the second one, the blue represents the exponential base function of 2 to the x, but now we have moved it over by 2 units to the right, so we have a horizontal shift. Notice that that is with the x in the exponent. All right, we're going to see what the impact A has on our graph. We're going to fix the value of B, the base, at 3. We're going to look at 3 graphs. The first one is just the base of 3. The next one is multiplied by an A of 5. And the third one is multiplied by an A of 10. Notice that the y-intercept becomes the A number in these cases. So the curves do become steeper, but for the second value, your y-intercept is 5, and for the third value, your y-intercept is 10. Okay? Here we have the transformations of graphs of exponent functions. So if you put a negative in front of your base, you get a reflection over the x-axis. If you have a negative with your exponent, you get a reflection over the y-axis. Okay? So here's one graph that shows a reflection over the x-axis for 3 of these. So where A is negative, the curve is reflected over the x-axis. Notice the y-intercept becomes the negative of the A value. So -1, -5, or -10. Alrighty, let's think about the transformations we've done from the past and how it looks now. They're actually all the same. So a vertical stretch at the A is greater than 1, the steeper the curve. If you have a that is a fraction, then the curve becomes shallower. And our reflection is always given by, that's right, a negative. The horizontal shift left is always given by an h that is what? Yes, x plus h, you move left. While if you do a horizontal shift right, it's x minus h. Okay? A vertical shift up is always a positive k, and the vertical shift down is always a minus k. Alrighty, we're going to go through some of these, and we're going to do some examples. Our parent function is f of x is equal to base 2 to exponent of x. We're going to state the domain, the range, and the horizontal asymptote for each, as well as the transformation. So what is the transformation for this? That's right. We have a vertical shift down 5 units. What is the domain? The domain is usually negative infinity to infinity for our exponential functions. What is the range? The range in this case has been moved because we have moved vertically down to a negative 5. What is the horizontal asymptote? That's right, the horizontal asymptote is negative 5. Let's take a look at this transformation. We have 2x plus 1. What is the transformation? The horizontal shift 1 unit left. What is the domain? Yes, negative infinity to infinity. What is the range? We didn't move vertically, so it's 0 to infinity, which means that the horizontal asymptote is y equals 0. Let's take a look at these transformations. What is the transformation? The transformation is a decay curve because it's been transformed over the y-axis, and we have a vertical shift up 4 units. What is the domain? That's right, it's negative infinity to infinity. What is the range? The range is from 4 to infinity. What is the horizontal asymptote? That's right, it's 4. All right, let's take a look at our last one. What is our transformation? This is reflected over the x-axis because we have a negative in front of the base number, and we have a horizontal shift to the right by 3. What is the domain? Still negative infinity to infinity. What is the range? The range here changes because we have reflected over the x-axis, which means we're negative infinity to 0. What is the horizontal asymptote? Yes, the horizontal asymptote is y is equal to 0. Which graph represents the transformations from the parent function of 2x? Look carefully. That's right, it's B. B reflects all the transformations accurately. All right, now we're going to take a look at how to use exponential functions to solve problems. Let's take a look at this one problem. Technetium 99M is a drug taken by a patient and then used to study tumors in the brain, lungs, and other parts of the body. A patient takes a 1,000 milligram pill. The data below shows how much active ingredient remains in the body over 6-hour time intervals. So you can see in the data at 0 hours, you still have 1,000. At 1 hour, it's 500, 2 hours is 250, and 3 hours is 125. What is the initial value? Yes, the initial value is A equals 1,000. Is this a growth or a decay factor? Yes, this is a decay factor. What is your decay factor? That's right, the decay factor is your base is equal to 1/2. We're going to write the rule. Notice that the A is 1,000, so it goes in front of our base, and then we just have an exponent of x. Let's take a look at one more example here. In television shows and movies, you often see scientists studying patterns of data, growth of zombies, bacteria, etc. Below is a table that shows the number of zombies over a 4-day period. Okay, so we have days 0, 1, 2, 3, 4, and then we have the number of zombies. They go from 2 to 8, 32, 128, and 512. What is the initial value? That's right, A is equal to 2. Is this a growth or decay factor? That's right, this is a growth factor. And what is that factor? That factor is base is equal to 4. So we're going to write the rule of the function. So our function is equal to 2, the initial value, times the base 4 to the exponent. Thank you for your participation, and that's all, folks.